Moving away from differentiation, we're going to start taking a look at the idea of partial integrals and the idea of iterated integrals. And let's say for some reason that we want to have a function of x in two variables and it's bound by this disk or this region R, where this is the x bounds and this is the y bounds. The notation, if we have this c to d of fxy dy, that means that we're going to hold x constant. So basically just pretend the x isn't there, or you could factor the x on the outside of the integral, and you could integrate with respect to y. Now, if x is embedded within another function of y, then you can't factor that out. So for instance, if you had something like cos of x squared plus y, then unfortunately you couldn't factor that term out. But if it was just cos x squared, you can certainly put that on the outside. Anyhow, for some reason you want to evaluate a double integral, then a double integral is essentially going to be two integrals placed into one problem. And so we have this structure, and the order of integration goes from inner to outer. So this would be the first integral with respect to x, and the dy would be the second integral. All right. Now, believe it or not, later we're going to do triple integrals, so the order of integration most certainly matters. All right. Also note that you can flip the order as long as it's just in terms of just x and y. So if the bounds are numeric. Now we're going to see later in the course that we're not allowed to just flip the bounds if the bounds are in terms of one of the other variables. All right, but we're going to see that we can do it, just we're going to have to do more work. But as long as a, b, c, and d are constants, or they're not contingent upon other variables, then we can just flip the order. So notice right here we have c to d dx as the first operand and c to dx as the second operand, and that's called Fubini's theorem. So we're just going to take a look at how to mechanically operate on these double integrals to start with, and then we're going to go through, we're going to use the midpoint rule to approximate these values. So a really basic example, this 0 to pi halves, 0 to 2, 3x squared cos y dy dx. Now notice dx is on the inside. Another way that we could write this, not that you have to do it, but just to give you an idea, is you could write this as the integral from 0 to pi halves of cos y dy, 0 to 2, 3x squared dx. And that's only true if the bounds are constants or they're not in terms of x or y. All right, so be careful with that. It doesn't work all the time, but in these first examples where we're just working with constants, it most certainly works. Right. Now we can go through and evaluate each integral individually. Antiderivative of cos is going to be sine, so we get sine of y from 0 to pi halves. And then we get 3x cubed over 3 from 0 to 2. And using our fundamental theorem of calculus, we get sine of pi halves minus sine of 0 times 2 to the third minus 0 to the third. Right? And this is going to work out to be 1 minus 0 times 8 minus 0, otherwise known as 8. All right, so a really basic example as to how to start to be able to evaluate these double integrals just to see the process. Now they're not always that easy. A second example. Now this is a function that we can't break apart initially. So we have this double integral of sine x plus y dx dy, where r is bound by 0 to pi halves in x and 0 to pi halves on y. So we're going to set this up. 0 to pi halves, 0 to pi halves. We have sine of x plus y, and in this case it really doesn't matter because the bounds are all the same. Right? Now, this is a sneaky one, but you can do a u sub. So if u is equal to x plus y, and you're differentiating, with respect to x, then the derivative of u is 1 du. The derivative of xy with respect to x is going to be 1 dx. And that's exactly what we want. We want 1 dx, and we want 1 xy. So now we can rewrite this, 0 to pi halves. We're going to use dummy variables, a to b. Instead of x plus y, we have sine of u. Instead of dx, we have du. And this dy is going to kind of carry down there. Alright, now notice we didn't break it apart because sine has a y inside of it. Alright, so we can't really factor that out. Alright, or just rearrange it. And so now we know the antiderivative of sine is cosine, negative. So we now have 0 to pi halves, negative cos u from a to b dy, or integral 0 to pi halves of negative cos x plus y. And let's just make a note of this, that this is when x is equal to 0 and x is equal to pi halves. And that's going to be dy. Right? And now we're just going to substitute, and we're going to get a single integral. So 0 to pi halves, we're going to have negative cos of pi halves plus y, and then minus a negative cosine of 0 plus y, and that's dy. Now clearly the second term is just cosine. All right, so let's just erase this now that you've seen it, just to save a little bit of room. And we can just rewrite that as just cosine. So it's just going to be plus cos of y. Right. Now we can integrate this. Right. If you wanted to, you could do another u sub on this, but because the interior term is all linear, we know that's just going to turn out to be negative sine of pi plus y, or pi halves plus y. And so let's just go ahead and integrate. So this is now going to become negative sine, since the antiderivative of cos is sine, negative sine of pi halves plus y plus sine of y from 0 to pi halves. Alright, and now we just substitute for pi halves. So this works out to be minus sine pi halves plus pi halves plus sine of pi halves minus, now we're going to substitute 0, negative sine pi halves plus 0 plus sine of 0. Alright, and now this looks ugly, but there is some good news about all this. Alright, so we know that the sine of any multiple of pi is going to be 0. So sine of 0, sine of pi, sine of 15 pi. So right here, this is just pi, and sine of pi is 0. Sine of 0 is 0, so those just go away. We know that sine of pi halves is 1, and right here we have another sine of pi halves. So that's going to be 1 as well. And this turns into a double negative. So we have 1 plus 1, and by advanced numerical methods, 1 plus 1 works out to be 2. Great. So just two really basic examples for you all to introduce you to these double integrals. One example we could very easily separate. Another example, because the function was dependent upon both x and y in the interior, we couldn't separate. We're going to take a look at one more basic example, and then we're going to use the midpoint rule in the next video.